Greetings A-level students, welcome to today's video which is all to do with acids and bases. One of the best topics in year 13. So, we need to know some definitions about what an acid is and what a base is. We're not going to use the Arrhenius definition or sadly the G.N. Lewis definition, Gilbert N. Lewis, one of my favourite chemists. We are going to use the Bronsted-Lowry definition. So Bronsted was from Denmark and Lowry was from Blighty. So this was an international effort, and because of this they get their names attributed to these definitions. So we got to define an acid. An acid under this definition is defined as an H+ donor or a proton donor. So it's any species which gives out an H+. So for example, if we take HCl, we dunk it into some water, AQ, that ionizes to liberate H+, and Cl- ions. Now this is an oversimplification, okay, because really what is happening, that H+ is too small and highly charged to exist on its own. What's really going to happen is that the HCl, when it goes into water, we get the hydroxonium ion forming and the Cl- ion. So when we get to it, we've got some conjugate acid-base pairs, and this is called a hydroxonium ion. But for simplicity, we normally just use the top version. Hydroxonium ion. And by the way, we can link this to shapes of molecules. In the hydroxonium ion, this is pyramidal. And we have one lone pair, bond angle of 107 degrees. And this species has a plus charge. Okay, so what is the definition of a base? Well, a base is defined as H+. Think about it. If an acid is defined as an H+ donor, then the definition of the base must be the opposite. That must be, rather than donating something, the opposite of donating something is accepting something. So a base is defined as an H+ acceptor. Okay, so let's just have a look at the above example. So let's take HCl and let's see it react with H2O. Well, we know that this species gives out H+, right? So if that's giving out H+, so here's my water molecule, and it's got two lone pairs of electrons, okay? So when HCl ionizes, we've got an H+ floating around, and look, what's going to happen? We're going to get a dative bond forming between these guys. So if this species is behaving like, so my HCl is behaving like an acid because it gives that H+, well, my water in this case is behaving like a base because it accepts H+, okay? So therefore, that's my acid, that is my base in this example, okay? And it is as simple as that. When you're doing acid-base questions, follow the proton. That's all we're doing, okay? Whoever loses it, that's the acid. Whoever gains it, that's the base. Okay, so let's have a look at what's going on here. And we're looking at conjugate acid-base pairs. All right, so in question number 1, let's go step by step. We'll start with the ammonia. So literally what's happened to the ammonia going from NH3 to NH4? Well, we've added a proton to it. If we've added a proton to it, the NH3 must be accepting a proton, so therefore that is my base. Okay, what's happened to my H2O? So my H2O has gone to OH-, so let's think about what's happened here. So this guy has lost a proton. If this guy has lost a proton or donated a proton, this must be behaving like an acid because it's giving out protons. And there are my acid-base pairs. Now, what we can do is we can go the opposite way, right? So if we go the opposite way, if I get rid of my arrowhead, in fact, I'll just go do it in a different color. So if I go from OH minus to H2O in the opposite direction, we're adding an H plus. So therefore my OH minus, if it's accepting an H plus, going from right to left, this must be behaving like a base. And then using the same logic, what's happening to my NH4 plus when it goes to NH3? Well, this is losing an H plus, so therefore my ammonium ion is behaving like an acid. So there I have my acid-base pairs on the left and right. Okay, so that's how I would do it. And then picking up a bit of speed, that is my acid and that's my base. And then this is my acid and that's my base. And then we can just yoke them and link the pairs. The H2O is a link to the H3O plus, and the HCl is a link to the Cl minus. Okay. Finally, the HCl in number 3 is my acid, and the ammonia is my base. Okay. Do we have acid-base pairs on the other side? Yeah, if I dissociate them, but we'll just do it for the reactant side. Sorted. Okay. So that's really useful, okay? Figuring out what's the acid and what's the base. Okay, so a bit of a GCSE recap on the pH scale. So in GCSE, you would have seen a relationship between the hydrogen ion concentration and the pH. So pH is a measure of the hydrogen ion concentration. So pH is a measure of the hydrogen ion concentration, square brackets. And what's happening is, so if we have a pH of 1, the hydrogen ion concentration is 0.1. Now, if we take that number and divide it by 10, we get a new hydrogen ion concentration as 0.01. And look what's happened to the pH as we get less concentrated in terms of the hydrogen ion concentration. The pH has increased by 1 unit. And then if we decrease the hydrogen ion concentration by a factor of 10 again, so we're getting more dilute, so less concentrated, look, the pH is going up by 1 unit. So using that logic, and it's useful not to forget this. So let's say we've got a hydrogen ion concentration of 1 times 10 to the minus 3, and we're going to 1 times 10 to the minus 5. So if we divide by 100, the pH has gone up by 2 units. So the lower the pH, the higher the hydrogen ion concentration. Okay, don't forget about that relationship. And then taking it one step further and not going into the maths of it, well, we can have an A-level definition for what pH is. So we'll get our calculators up in just a second, but anytime they ask you, don't write it in extended prose. pH is defined as the negative log base 10 of the hydrogen ion concentration. Technically, I should put the hydroxonium ion concentration, but it's easy putting H plus, okay? Okay, so let's get our calculator up. Okay, all we're going to do is use this formula. So if the pH is 0.1 moles per decimeter cubed, what we're going to do, that tells us, so the hydrogen ion concentration is 0.1 moles per decimeter cubed. If I look at that equation, I have this term. So all I have to do is use that equation. So to convert that into pH, I'm going to do minus log base 10, stick this number in, which is 0.1, and let's see what we get. Now, I know you can all do this. I know you know what the answer is before putting it into the calculator, but it's useful to know how to set it out. So hit the minus button, find that log button and put base 10, and then stick the hydrogen ion concentration, and there you go, voila, it is pH of 1. Normally quote pH to 2 decimal places, okay? So let's have a look at example 2. I am given the hydrogen ion concentration So then the pH is going to be equal to the negative log base 10 of that value that I just substitute in. And we will need our calculators for this. So minus the log base 10 of 5.6 times 10 to the negative 4. And I get a value of 3.25. Done. That's it. So now what we're going to practice is we're going to calculate the hydrogen ion concentration from the pH. And another equation that we need to remember is that the hydrogen ion concentration is equal to 10 to the power of negative pH. So remember that equation, guys. Very useful. So I know the pH now, so I know that term. So all I do is substitute that value in. So my hydrogen ion concentration is 10 to the power of minus 2.80. And let's see what we get. So how does this look on a calculator? So if I press Shift, log button, that gives me 10 to the power of, and that is the anti-log, I guess, or to unlog it, if that's a word, and that gives me the hydrogen ion concentration as 1.58 times 10 to the minus 3 moles per decimeter cubed. And we're going to do the same thing for example number 2. So my hydrogen ion concentration is 10 to the power of minus 12.80. So Shift log minus 12.80, and I get a hideously small hydrogen ion concentration. It's so small, it's 1.58 times 10 to the negative 13 moles per decimeter cubed. It's very alkali. I know that because the pH is greater than 7. Okay, let's now have a look at some questions. Okay, so we've looked at strong acids and how to determine the pH of strong acids. We just have to use the equation for pH. And we've looked at weak acids as well. But now what we're doing is we're determining the pH of a solution when we're mixing a strong acid and a base together. Okay, so let's think about this. If I just had, we'll do it in 2 steps, okay? Now, if I just had H2X when I'm looking at this, if I just had H2X, then what I'm thinking is if the H2X fully ionizes, I'm going to get 2 protons and 1 mole of X2 minus ions, okay? If it's a strong acid. So, I'm going to show you 2 things here. One, just determining the pH of the strong acid when it's diprotic or dibasic, and then we'll look at the question where we're mixing the 2 together. All right, so if I have 0.15 moles per decimeter cubed of the H2X, the concentration of the hydrogen ions is going to be double that, so it's going to be 0.300 moles per decimeter cubed. So then I would just stick this into my equation for pH. And what do we get? So if I take the negative log base 10 of 0.3, yep, it's very small pH, very acidic, 0.52. Okay, so that's how I'd work out the pH of the acid. But what we're doing here is we are adding 2 of the species together. So we're mixing an acid and a base. Okay, so I'm going to rewrite my dissociation equation. Okay, I'm going to rewrite my dissociation equation. So my strong acid, that I label SA for strong acid, splits up into 2 protons and X2 minus. And then I look at my base. So that is simply KOH. So if that's a strong base, so that is going to be KOH, which dissociates into K plus and OH minus. Okay, so now what I'm going to do is I'm going to work in moles. So let's work in moles. So I'm going to work out the number of moles of H2X. And to do that, remember N equals C times V. So, got the volume, it's 25 over 1,000 multiplied by 0.15. And what does that give me? I'll get rid of my calculator to make a little bit more space. So, we get an H2X number of moles as 3.75 times 10 to the minus 3. So then, to work out what my number of moles of protons is going to be, I'm just going to double it. So that's going to be 7.5 times 10 to the minus 3. So I've just worked out the number of moles of H+. Okay, then I'm going to do the same thing for the KOH. So I'm interested in the OH minus here. That's why I wrote out the dissociation steps. So I'm going to work out the number of moles of KOH. It's 50 over 1,000 multiplied by 0.1. So does that give me 5 times 10 to the minus 3? Yes, it does. So then to work out the number of moles of OH minus ions, because the ratio is 1 to 1, it's also going to be 5 times 10 to the minus 3. Nice. Okay, so then when these guys actually react, we have got the acid reacting with the alkali. And when the acid and the alkali react, it's neutralization. It's a neutralization reaction. And in neutralization reaction, we can simplify the reaction to H plus OH minus goes to H2O. And now I'm just going to use the number of moles here. So for H plus, I know what it is. It's 7.5 times 10 to the minus 3. And for my OH minus, it is 5 times 10 to the minus 3 in terms of moles. Okay, so now it's a limiting reactants problem. And the ratios are 1 to 1, so I can straight away identify this as being the limiting reactant because there's fewer moles. So if that's my limiting reactant, then by definition the other one is going to be my reactant in excess, and some of that's going to be left over, right? So I'm just going to put excess. So this is going to go down by 5 times 10 to the minus 3 moles. And that also goes down by itself. So I'm going to have 0 moles of the OH minus left after the reaction. So how many moles of the H plus do I have? So that should be 2.5 times 10 to the minus 3 mole. Okay, so then where do we go next? So I know my acid is in excess. Great. Let's put a box around that. There we go. So now I need to determine the concentration of H plus ions. And look, when I'm determining the concentration, I now have 2 volumes added together. So my V tot is going to be 25 plus 50 over 1,000. Okay, so this is going to be 75 over 1,000. So this is going to be, what is it going to be? So that's going to be 0.075 decimeters cubed. 1, 2, 3. Yeah, perfect. Okay, so now I need to work out the concentration of H plus ions. So that's going to be 2.5 times 10 to the minus 3 over 0.075. And what does that give me? So let's process this. So if we process all of that, we get 0.033 moles per decimeter cubed. Okay, so that's the hydrogen ion concentration. So now I need to determine the pH. So remember that pH is defined as the negative log base 10 of the hydrogen ion concentration. So if I stick that number in, what do we get? So negative log base 10 of that answer should get a pH of 1.48 to 2 decimal places. Okay, and there you go. That's how you determine the pH of a strong acid versus strong base when the acid is in excess. Okay, we've also got an example of where you can do it for a strong acid and a strong base when the base is in excess and you have to use kW, but there is a video on that and it also links to buffers. All right, thank you very much for watching. Ta-ta.